One of the most groundbreaking experiments in the history of physics was conducted to test Bell's inequality theorem. The results sent shockwaves through the scientific community and firmly established quantum mechanics' strange, non-local nature. This wasn't just a test of mathematical predictions, it was an investigation into the very nature of reality itself. Let's dive into the fascinating story of the experiment that disproved Bell's inequality and what it means for our understanding of the universe. In 1964, physicist John Bell proposed a theorem to address a key question in quantum mechanics. Is reality fundamentally local, or is it governed by the spooky action at a distance, predicted by quantum entanglement? Locality, the principle that objects are only influenced by their immediate surroundings, and no information or influence can travel faster than the speed of light. This principle aligns with Einstein's theory of relativity. Quantum entanglement, a phenomenon where two or more particles become so deeply correlated that the state of one particle instantly determines the state of the other, no matter how far apart they are. Bell's theorem showed that if the universe followed local realism, a combination of locality and the idea that particles have predetermined properties, then there would be a strict mathematical limit to the correlations observed in measurements of entangled particles. This limit, known as Bell's inequality, provided a way to test whether quantum mechanics predictions or Einstein's views of locality were correct. In the early 1980s, Alain Aspect, a French physicist, designed and conducted an experiment that would become one of the most significant tests of Bell's theorem. Aspect's work built on earlier experiments by John Clauser and Stuart Friedman, but it introduced a critical improvement: the ability to switch measurement settings during the experiment. This eliminated potential loopholes and strengthened the results. Aspect's experiment involved entangled photons, particles of light whose properties, such as polarization, are correlated. Here's how the experiment was structured. 1. Photon source. A special device produced pairs of entangled photons. These photons were emitted in opposite directions toward two detectors. 2. Detectors. Each photon traveled to one of two detectors, located far apart. These detectors could measure the polarization of the photons using filters set at various angles. 3. Measurement settings. The angles of the polarization filters could be adjusted during the experiment. Crucially, the settings were changed so rapidly that the photons couldn't know the other detector's settings, ensuring no communication between the particles or detectors. If local realism were true, the correlations between the polarization measurements would respect Bell's inequality, staying within its predicted limit. If quantum mechanics were correct, the correlations between the entangled photons would violate Bell's inequality, demonstrating stronger than expected connections. Aspect's experiment showed that the correlations between the entangled photons violated Bell's inequality. In other words, the results were consistent with quantum mechanics and not with local realism. The photons' measurements were more strongly correlated than local theories could explain. This meant that either locality or realism, or both, must be abandoned. The experiment demonstrated that 1. Non-locality is real. Aspect's results confirmed that quantum mechanics is inherently non-local. When two particles are entangled, their states are connected instantaneously, no matter the distance between them. This phenomenon does not involve the transmission of information faster than light but reveals a deep and mysterious link between entangled particles. 2. There are no local hidden variables. The experiment ruled out the possibility of local hidden variable theories, which suggested that particles carried hidden instructions, determining their behavior. The results showed that the outcomes of measurements are not predetermined but emerge only when the measurements are performed. 3. Quantum mechanics is complete. Aspect's experiment reinforced the idea that quantum mechanics provides a complete and accurate description of the physical world, even if it defies our classical intuitions. 4. The nature of reality is stranger than fiction. The results of the experiment forced physicists to reconsider fundamental assumptions about reality. The idea that particles can influence each other instantaneously challenges our understanding of space, time, and causality. While Aspect's experiment was groundbreaking, physicists continued refining the tests to address potential loopholes. The communication loophole: could the detectors or photons somehow exchange information? Later experiments increased the distance between detectors to billions of times the size of the particles, closing this loophole. The fair sampling loophole: could the results be biased by unmeasured particles? Advanced experiments used more efficient detectors to ensure that nearly all photons were measured. The free will loophole. Could the experimenter's choices of settings influence the results? Recent experiments have used random cosmic events, like distant starlight, to determine measurement settings, ensuring no human influence. Each successive experiment has confirmed the violation of Bell's inequality, further validating quantum mechanics. The validation of entanglement has paved the way for revolutionary technologies, including quantum cryptography, ultra-secure communication that uses entanglement to detect eavesdropping; quantum computing, machines that leverage entanglement to solve problems far beyond the reach of classical computers. The experiment also challenges our classical view of the universe. It suggests that reality at the quantum level is interconnected in ways we don't fully understand. The implications touch on profound questions about the nature of existence, causality, and free will. The experiment that disproved Bell's inequality wasn't just a test of mathematical predictions, it was a journey into the heart of the quantum world. By confirming the strange, non-local nature of reality, it shattered classical assumptions and opened the door to new technologies and philosophical debates. As physicists continue exploring the quantum realm, one thing is certain: the legacy of Bell's theorem and Aspect's experiment will remain a cornerstone of modern science, forever reshaping our understanding of the universe. The universe isn't just stranger than we imagine, it's stranger than we can imagine.